Okay, I think we are rolling. Welcome, everyone. Thanks for tuning in again. Another episode of the F Word. Um, as I was working on this material for this week, it's just there's a lot of information. So this is probably going to be a multi-parter. And I know the description for this one says we're going to talk about nonlinear, and I might do that to some extent, but we're going to focus right now on the linear Euler implementations we have because those are actually um, now merged into the main branch of self. We've got some things that we actually understand, like what's going on there. Anyways, I'll kind of walk through a lot of the details in self as well. So I'm hoping that this kind of like answers how we're doing um, some of like the highly flexible stuff we have in self using object-oriented Fortran. But yeah, that's kind of where it's at. So yeah, like I said, this might end up being a two-parter on this one. So you'll probably see this a similar title coming up in an upcoming stream. So let's dive into it here. So you might remember from before, this is how self views a partial differential equation. We cast a PDE in terms of an arbitrary conservation law, where you have S, the vector S is a vector of prognostic variables. F is the what's called the flux divergence, or divergence of F is the flux divergence. F is the flux. It's a vector of vectors, and what I mean by that is each prognostic variable has a vector in space associated with it that tells us what the conservative flux is. So that's why we're using that double arrow notation there. And then on the right hand side, there are source terms. Now that flux could be, typically it's a hyperbolic flux. That's dominantly what we work with. We do have some stuff built in to work with parabolic fluxes. So if your flux depends on the gradient of your variables, that's permissible as well. In self, at this point, everything is done with discontinuous Galerkin method. So we basically weight that conservation law by some test functions and then integrate over the elements in the mesh. On that flux divergence term, particularly, we do integration by parts once. So we separate out the flux into what's called the surface flux. This is where the Riemann solver is specified, and then you have volume flux terms. Now, there's a lot. So this is like what I've shown you so far is the continuous form of the equations. To get to the discrete form, essentially space is broken up into elements, and within each element, we treat the solution, fluxes, and source terms as Lagrange interpolating polynomials. Those Lagrange interpolating polynomials have interpolation knots at Gaussian type quadrature. And so when you make all those assumptions and you plug it in, that reduces to a discrete system of equations that approximates the original conservation law. We also do coordinate system mapping, so you can do some pretty complex stuff. And I'm hoping at the end here, I have running in the background something that's rendering one of our demos of just a simple simulation of some sound waves rattling around the inside of a mesh that's shaped like a pumpkin. So that'll be fun. All right, so if we cast things in terms of this arbitrary conservation law, what we need to do to define a problem is to define the flux vector and the source terms, and then there is some options to set metadata so you can describe what the prognostic variables are, which makes your output files look nice and neat. So for like linear Euler 2D, this is what we're working with here is the prognostic variables over here on the left. We have the density rho. We have the two velocity components u and v, and then we have the pressure that's tracked there. For the flux term, we have for the density, we have advection, it's really just fluid divergence. So it's rho naught, some background reference density, and then the velocity field there. And then the only terms on the right-hand side for the momentum equations is going to be caused from pressure gradients. The way you can implement a pressure gradient using a flux divergent is just to take for the x direction the scalar p and multiply by the x hat vector. Same thing for the y direction. So this effectively gives us a pressure gradient force that's implemented for the u and v components of the momentum equation. And then the last equation, if we assume an ideal gas, so P equals rho RT, and we assume that RT is speed of sound squared because from thermodynamics, dP rho is c squared, speed of sound. You can get an equation for the pressure. So this is how you close that system. We are not considering any source terms right now, but you could imagine if you have like gravity or those kinds of things, you could stick that there. And then for the Riemann solver, for those surface fluxes, we're basically going to be taking an average of the fluxes on either side of an edge. So when the two elements share an edge, you have two predictions of the solution on either side. And what you need to do is reconcile that by exchanging mass and momentum and energy fluxes. Here we're going to just be using a simple local Lax-Friedrichs, which is taking the average of the fluxes, computing the left and right states. And then we add to it a difference of the solution, or the jump in the solution on the two sides, and that coefficient out front there is going to be the maximum wave speed. For linear Euler, that's nice and easy because that's just the speed of sound. So we can do that. Now, I know I'm sitting in front of it. Maybe I go this way. All of this is documented at self.fluidnumerics.com. We just published that documentation up there. So it's got the complete descriptions for this system, as well as some descriptions of the examples that are available. So that's that. Now, I did want to talk about the time stepping pipeline because it occurred to me that in the last few episodes, I haven't really talked too many details about like what can happen when you put this on the GPU. So I want to give you some ideas of like what's actually happening there. In Self, I mean there's a lot of files, but we're going to start by talking about there's a file called self model. This is self-model.f90. It defines an abstract class that all the other models in Self are based on. And that abstract class is what gives us a lot of the templating for progressing a model forward in time, for moving a conservation law forward in time. Now, if of course, if you do a type extension of the model class, of course, you can override all of this stuff. There's nothing that can stand in your way to do that, but we provide a lot of these templates as a convenience because they'll fit the majority of conservation law implementations from our perspective. That's what we've seen so far. And where like the main method, the main workhorse method that really drives a model forward in time when you're running your simulation is this forward step method. In every single one of our test programs that's testing one of the models, you'll probably see a call to forward step. And the way that forward step works is, at least in the model class, it's set up to basically call a bunch of abstract methods that when you define a child class, like the DG model 2D or the Euler class or linear shallow water, those methods that are abstract at the model level are then concretized, which is what really sets up what's needed to calculate the tendencies according to the PDE that you want to solve. But this just gives you a nice framework that you tell me the time that you want to iterate to. So you have your starting time and your end time. You tell me how frequently you want to write the model state out to file. And this procedure takes care of that. So what basically this is it. This is all the code that's there. Is you have a do loop over the number of iterations to go from T0 to Tn. And then each one of those, what we're going to do is move forward a time integrator from one file to the next inside of that sort of macro level time stepping. And you'll see I have these comments in here. It says that the time integrator is abstract-ish, and I'll explain what that means here in a minute. So we basically call the time integrator. This could be like, forward Euler. This could be Runge-Kutta 2, 3, or 4. I think at one point we had Adams-Bashforth, but the time integrator classes, or the time integrator property. Oops, I don't want to jump too far ahead. The time integrator property it's a procedure pointer that allows you to set the time integration scheme dynamically, just using procedure pointers, which is kind of cool. So like if you end up defining your own time integrator that matches the API that's required, you can actually point your model to your own time integrator, which we find is kind of cool. Once the time integrator goes from one file output level to the next file output level, it'll write the model. Now that write model class, we provide a write model class for you for 1D, 2D, and 3D. And those will just take like the metadata for your solution state, and stick those in HDF5 files using a format that we have defined. I think I don't know if we've gotten around to it quite yet, but it is on our checklist to get that format documented. But we are also working on like Python utilities, so you can like load those in Python and do a post-processing analysis that way. We do have optional tech plot files that can be dumped, which is quite helpful if you have like ParaView or Visit. Again, these are abstract at the model level, because once at this stage, we have no concept of 1D, 2D, or 3D. Basically, write model and write tech plot end up getting concretized one level down in the DG model 2D, 1D, 2D, and 3D classes. From there, there's an I/O counter that's incremented just so that the output files have the correct timestamps on them. And there's another abstract-ish method here called calculate entropy. Again, I'll explain the ish here in just a moment. And then there's some built-in stuff, report entropy. So every model has what we call a mathematical entropy. You might think of this really as like the total energy of your system in a lot of cases. But this is just a way to report back to the user, stability information to make sure your model hasn't blown up, those kinds of things. I have just put this in recently, so it's not in main yet, but the report user metrics provides you a way to put your own custom metrics out to standard output in that time stepping pipeline. That's basically it there. Now let me talk about abstract-ish stuff and the time integrator. So when I say abstract-ish, it means that like I do have a method in the model class that does this, but that method itself depends on abstract methods. So the time integrator, again, it's a procedure pointer. So it's part of the model class, but you can point that procedure to anything that matches this API. So you basically need to have as input, or in-out, you need to have a model coming in and out, and then you need to just have this real variable tn, which is the final time you want to get to, as the input. Everything else inside of here, if you wanted to write a time integrator that suited your needs better than what we've provided out of the box, you can easily do that and then point the model time integrator to your own subroutine. Again, so this method depends on abstract methods. The two abstract methods here, there's calculate tendency, which basically is the thing that calculates the divergence of the flux in weak form, and the source terms. And I'll spend a little bit of time explaining the pipeline inside of calculate tendency, because that should help you conceptualize like all the steps that are required to actually move these models forward in time. So if I were to summarize here real quick, we have at the top level in the model class, we have this thing that forward step stuff. This is usually what you call to drive your model forward in a program that uses self. Inside, what's actually happening is it's calling a time integrator. It's writing out files, and it's reporting entropy and user metrics back to the screen for you. We've provided a few things that you can override so that you can customize like what's dumped out to screen, what's actually written to your files, things like that. And again, the time integrator, we do provide out of the box Euler, RK2, RK3, RK4. That those methods, although they are concretized in self-model, they're abstract-ish in the sense that they will depend on abstract methods that are concretized in the next level of modules in self. So these are the DG model 2DT classes, 2DT, 1DT, 3DT, etc. So let's take a look at one of those tendency methods. This is what it looks like for the 2D problem. It's very similar between 1D, 2D, 3D. The main difference ends up being this this do concurrent block to update, like basically combine the source and the flux terms. I suppose there'd be a way to really push all this into self model, but this is how it's done right now. So the way this the calculate tendency works is on the outset, what we assume is that what we have as input is a model. So in this case, the DG model 2D class that has the solution attribute defined at all the quadrature points. And what our job is to do in the tendency pipeline is to use that information to calculate flux divergences and source terms. Okay, so flux divergences depends on fluxes at quadrature points within the elements, and it depends on the Riemann fluxes on the surfaces of your elements. So in 2D this would be on the edges, and in 3D this would be on the faces of all the elements. So the first thing we do is this boundary interpolation, and you might be thinking, well, isn't that extrapolation? I mean, we can mince words about it, but essentially, if you're on Gauss points, the Gauss points are always interior to a computational domain of -1 to 1 in each direction. So they're not already, the solution's not already on the actual element boundaries. But the Lagrange interpolating polynomials are defined on the domain -1 to 1. So like we already have that information, but we basically need to move from the quadrature points to the boundary points. So that's what that does. And the next method does what's called a side exchange. So side exchange takes the mesh information that we have, and we have in that we have knowledge of who's neighbors, so which elements share an edge or which elements share a face, and we use that mesh information to take the boundary information from the elements and send it to your neighbor to store in another table. That's where all the MPI magic happens underneath the hood for you. So basically, once we've gotten past boundary interp and side exchange, every element knows, every element has awareness of what its solution is on its element boundaries, and it has information about what its neighbors' values are on the boundaries. The next bits here are these user supplied. These are, I guess I could have labeled these abstract-ish because they're the same, like they are defined in the DG model 2D class. But inside of there, basically what we have provided for you is loop structures that you might not want to know about or care about unless you're really trying to drive for performance. The basically set boundary condition, calculate solution gradient, set gradient boundary condition, etc. These provide loop structures and standard things that we have baked in, so that all you have to do when you concretize your model is to define some simple pure functions that take knowledge of the solution and the solution gradient at a single point, and you can return like the flux, the source, the boundary condition, for example. But as part of the pipeline, okay, so we do boundary interpolation, we do side exchange. This pre-tendency, honestly, this came about for a number of reasons. For example, and I guess I won't get into too many details, but the nonlinear Euler equations, you usually model the conservative variables. So this would be density, momentum, so rho times u, rho times v, and total energy. But like if you want to calculate parabolic fluxes, what you need are primitive variables. You need u, you need v, and you need to be able to go from conservative variables to primitive variables. Those additional kind of things you ideally want to do in this pre-tendency method. And the intention here is that, like, if you don't override it, it does nothing. But if you do override it, you can add additional calculations that you want to have happen further down in your pipeline. Then there's, of course, set boundary condition, which we have talked about a couple times before. But I suppose every one of these kind of deserves their own video explanation. If gradients are enabled, we have a standard pipeline for using a Bassey-Rebay method to calculate gradients. So Bassey-Rebay, essentially what that does is you're going to use, so you're still going to do a weak form of the gradient, and on the boundaries, what you're going to use are the average of the state that your element has and the state of what your neighbor's element has at the boundary for the solution value when you're calculating the boundary flux terms for your gradient. Then, of course, once we calculate the gradient, we do go through and set gradient boundary conditions that you can also specify, and then we spit out an average of the gradient at each of the sides. Because typically, when you do divergence of I should say not typically, but when you do a Bassey-Rebay method for divergence of parabolic fluxes, you're basically using both the average of the solution to calculate the gradient, and you're using the average of the gradient to calculate the Laplacian. So that's what goes on there. The next three bits are source methods, so specifying that Q vector on the right side of your conservation law. Boundary flux, this is where your Riemann solver is done, and then your volume fluxes, so the flux method. So that's the standard pipeline. Basically, once we have all that done, the rest of self takes over, so it does the map DG divergence. And if you remember from last week, I kept like harping on it. This guy is definitely the workhorse. It takes the majority of the runtime to actually do. All of these up above are point-by-point calculations, so they're easy to parallelize for the most part. I mean, when you get to nonlinear stuff, it gets kind of funky, but at any rate, most of the work happens here, and then we just combine the source and flux divergence terms to then kick back to the time integrator. So that's the time stepping pipeline. Let's take a look. I do want to show you what I mean by user supplied here. I guess the same thing could be said. It's abstract-ish. We provide do loop structure for you, so you don't have to think about it. So this is just the volume flux. Remember, this is done for set boundary condition, set solution gradient, set gradient boundary condition, source method, boundary flux, flux method. This is flux method in 2D. It's basically a do concurrent loop. And that guy is going to go over the first two dimensions here are the quadrature points within each element. And then the last loop iterator there is the elements. Okay. And all we're doing, and this is where it ends up not being super ideal on the CPU side, is we grab all the solution variables at each point. So we do some out of order indexing here. As well as we grab the gradients. So at each quadrature point within each element, we grab all the gradient variables, and then we just pass that to this flux2D method. That is that pure function that you usually override when you concretize your method. Again, the intention here was just to make it easy to use. It does do okay at performance, but in terms of usability, this is actually quite nice. On the GPUs, we actually override flux method, so we end up having the same thing. I think now I have this as a do concurrent. This is an old picture here, but we basically do the same thing, but then we have a method to update the what is seen on the CPU and GPU, and that's really needed for correctness, to make sure we have consistency between results on host and device. And again, while this is good for correctness, it's required for correctness, and it still allows you to just very quickly just rebuild self and target the GPU you want, and then link your program against the GPU accelerated build of self. You'll get the right answer. The performance is not going to necessarily be great because of all these additional mem copies that are happening. And you know, I was hoping to have some demonstration of that today. I've got some profiles I'm still reviewing, so I'll probably be looking at those in the next couple of weeks. I'll share those with you once I've got those sorted out. But you know, in reality, like if you want this to go really fast, you want your code to be fully GPU resident, and we've actually done this for the linear Euler 2D. Is you basically override flux method DG model 2D in your specific models class, and you just use that to call a GPU kernel that you write in C++. Again, we have examples on how that's done, and I think I was planning on doing that today just to pull that up for you guys. So we're going to look at some code. We're going to look at some Euler equation output on a pumpkin just to show you guys what we've got out of the box there. I did want to make a quick plug like I do every time. Before we look at code, here's a few ways you can support what we are doing. One, you're doing it right now. You're tuned in. You're checking out what we got going on. We really appreciate you being here. If you haven't already, you can subscribe to us on YouTube. Once you subscribe, you'll be able to submit your questions and chat with us through the chat on the live stream. We'd love to answer any questions you guys have. Of course, you can also use Self for your projects. We're always here to help. You can open up issues on the GitHub repository if you're looking for new models to be implemented. We just want to see Self get into as many hands as possible, and we'd love to help you get started with that. Give us a star on GitHub if you use Self, or if you just like what we're doing. You can also support our project on Open Collective. That QR code above me, if you scan that, that'll bring you to the Open Collective page. We are looking for people to help back this project so we can spend more time on it. We love doing this stuff. Of course, the other way is work with us. We are a company. We provide services. We do lots of cool things, cloud-related, Fortran-related, GPU-related, you name it. We love doing all the stuff that we're doing here. So those are the various ways you can make sure this stuff continues to happen. And now let's take a look at some code. Let me see here. I'll drag yeah. So I wanted to walk through what's going on in the linear Euler class. So again, remember what we want to do is, I guess we'll look at the CPU side first. To define the, that's nonlinear, let's do linear. To concretize our method, we really just need to override a few things. And aside from a few like boilerplate things up top here, like how many variables you have for your model and like the metadata you want to have. So these are just, just methods to set the labels for your variables, your prognostic variables. The main ones we're going to look at are entropy function. This is what we're using for tracking stability. We have HBC 2D, no normal flow. So this is hyperbolic boundary condition in 2D for no normal flow. And then we have the flux terms. This is our volume fluxes. So inside at your quadrature points, what the fluxes are going to be. And then we have the Riemann solver. So yeah, so number of variables here is 4, right? We have rho, u, v, and p. There's 4. And then in the set metadata, that's all we're doing is defining the names, the descriptions, and the units. Again, that just makes your HDF5 files like understandable. It's not just gonna be some generic solution 1, solution 2, etc. Report user metrics. That's a new feature. I'll talk about that soon. The entropy function for the linear shallow water that we're going to use is just the total energy. So it's the linearized internal energy, which is P on rho naught C squared. That's linearized internal energy. And then we have added to that the kinetic energy. So that's all that's done here. And again, the entropy function is a pure function. Takes in the solution state and it spits out a single value for the entropy. This is used, again, higher up in the stack. There's a multi-nested do loop that does a reduction for you. If you run with MPI, it does the reduction in parallel. So you don't have to worry about that. All you got to do is provide this guy. Boundary conditions for no normal flow. Again, if you check out the documentation, self.fluidnumerics.com, you'll see where all this comes from. But again, we're just overriding that so you can do no normal flow boundary conditions. Radiation is nice and easy because the external state for radiation and linear Euler is just setting all the variables in the external state to 0, which is already done by default from the parent class, so we don't actually need to override it. Flux method. So the way the variable ordering works, right, is you have the variable dimension first and then the physical space dimension. So x and y would be on the outside. So this first one here is, these first two are for the density. We have the x direction and y direction. So we just use u and v multiplied by rho naught. Oop, don't drag that. Yeah, for u, we just have p in the x direction. For v, we have p in the y direction. And for the pressure equation, right, we just do rho naught c squared multiplied by u in the x direction, multiplied by v in the y direction. And then here's our Riemann solver. So this really, like, honestly, you can run it you know, when we first implement a model, we'll just define the CPU version only and make sure it runs on the CPU, gets the correct answers for a few different test cases. And we can rebuild self with the GPU accelerated backends, and it still works. It still gets the right answer. Again, it's just not as optimal. And again, that's just because of the memory copies. So I want to show you what we did for the GPU accelerated version to give you an idea of like the amount of work that's required to get your code fully GPU resident. So let me go. So in the GPU, so in the source directory, there basically, you might remember, you might not. We have the base classes are defined at the bottom end of the source directories, and then for each backend that we target, we have classes that are type extensions of those that make specific assumptions about the architecture you're running on. In the GPU subdirectory, of course, there's going to be all the GPU accelerated stuff. So if I look under there and I see, here we go, self-linear Euler 2D F90, and then we have a CPP file that also has all the kernels defined. So I'll pull that open. So what we're going to do here is I'm going to do a couple things. So we're going to compare side by side what is going on. So the linear Euler 2DT, right? Nowhere do you see I'm actually overriding set boundary conditions on the right side. But remember, set boundary condition comes from the model class, or sorry, the DG model 2D class. Let me pull that guy up. The DG model 2D class has set boundary condition. Okay. And that guy, what he's doing is it's got our loop structure in it. It gets from the mesh the boundary condition IDs, my neighboring element, and then based on the boundary condition ID and if I'm actually at a boundary, it calls the right pure function to implement the boundary condition. So this is what makes it nice and easy to set up a model, right? Because you can just override these guys, these pure functions, and get things to work. But as I said before, when you do this on the GPU, we have to move data back and forth across the PCI bus, which is slow. So in our GPU accelerated version of the class, what we want to do is override those methods. So we want to basically implement what's done in the parent class, DG model 2D. So we have this method set boundary condition, and all that's going to do is call a kernel wrapper that launches either a CUDA kernel if you're on NVIDIA GPUs or a HIP kernel if you're on AMD GPUs. Okay, so that set boundary condition linear Euler 2D GPU. If we go down to the boundary flux, you can see that's all it's doing there is just calling that wrapper function. So if I look in the CPP file, all right, there's our boundary flux linear Euler 2D kernel. If you haven't written GPU kernels before, that's fine. I'm not expecting that you understand this. If you've done GPU kernels before, basically what we're doing is the outer loops, the J and the element loops, and actually this quadrature loop over the edges, we parallelize over those loops using the threads on the GPU, and then from there, based on the boundary condition ID, set the appropriate boundary. set the appropriate boundary condition. We basically have to do this for each of those methods, right? You have boundary flux, set boundary condition, and flux method. You got to write kernels for each of those. And once you override those three major ones, which if I go back to, let's go to calculate tendency. Once I override those, at least for the linear class, so what we've done is this guy set boundary condition is now fully GPU resident. We have source method. Well, that's not even being used. It's just doing nothing. We have boundary flux is GPU resident, and we have flux method, which is now fully GPU resident. And that effectively gets rid of all those mem copies that happen every single time step, and it does drastically improve the performance. So like I said, the easiest way to get started with any of this is just to assume you're building it for the CPU and override the pure functions and get that working. Once you have that working, and if you have access to a GPU and you can build self to target GPU architecture, you can then rebuild your program to link against your GPU accelerated libraries, and all the other stuff in self will just run on the GPU, and you will get the right answer. And that's a lot of cases. That's probably more than fine. But if you want help doing the extra bit of work to get it fully GPU resident, that's the kind of stuff we'd love to help you do. And if we see a model that's submitted to self through a pull request that has like the CPU side defined, it's very easy for us to go through and write those kernels. I think in the long term view of this, I would like to find an easier way to get GPU kernels up there, but like I just think with the tooling that we've chosen and where things are at here, this is kind of like as easy as it get. But I think the nice thing about this is there's just a clear recipe for how this gets done. I'm gonna pull up the documentation just to kind of walk through a couple of the examples that are included in self, and then I'll show you well, I guess I'll be surprised by what I see in the pumpkin simulation that we were just running before I started the stream. So if you're in the documentation, there's a tutorial section. And for each model that we build, we're actively trying to build out examples and tutorials and things like that. Under linear Euler 2D, we have 3 of them so far. Plane wave propagation. So this is a domain where all 4 boundaries are prescribed boundaries, and it just uses an exact solution for the initial and boundary conditions. Reflection is the same thing, except on the rightmost wall, we put a no normal flow boundary condition, and then for the prescribed initial and boundary conditions, we use a solution that's constructed from the method of images. Those are, yeah, so again, every one of our tutorials has an explanation of what the equations are. There's definitions of the model domain, initial and boundary conditions are defined there, and then there's some graphics that we've generated to show you how it works. Okay. Reflection, same kind of deal, except now we have a no normal flow wall on the right side, and you get a plane wave reflection. The graphics here are actually generated with a tool that we're actively working on. If you're on the main branch, you'll probably see a subdirectory called PySelf. We don't have documentation for it yet, but it's because it's still kind of actively coming together as we try things. The last one here we have for the linear shallow water is the spherical sound wave. So it's just a peak in the density and pressure. And this gives you a pressure gradient force that drives fluid away from the center of the domain and carries, mass with it. And as it does that, of course, it propagates like a sound wave. So you can, there's a lot of ways to check the correctness of these. So like the plane wave reflection and propagation, we have exact solutions for. So we're working on convergent studies there to verify we are getting spectral accuracy. As those details get documented, we will be posting those to documentation. Just really provides confirmation that what we have implemented is correct. For the sound wave, it's a little bit trickier. There is an exact solution, involves Bessel functions. We're working on defining the exact solution for that case so that we can do convergent study there. But some simple stuff. If we know the sound wave speed, you can estimate the arrival time of a pulse at that sidewall, and it gives you some confidence that it's doing the right thing. So again, where we're at is like we've got this implemented. It runs on CPU, GPU. We're building out examples. We're building out tutorials. We're working on convergence studies to verify everything is spectrally accurate, both on CPU and GPU and on multi-GPU environments. So it's a bit of work to like really be confident that what we have is right, but we're quite excited to finally get to this point with what we've got. Also been kind of jumping the gun a little bit and started implementing some nonlinear Euler stuff. So in the next few weeks, we'll be putting out some solutions for that. So you'll probably, if you're following the repository, every time the main branch gets updated, the documentation will get updated. So you'll see those tutorials come up as soon as we have those models implemented. Just a quick word on that. The nonlinear equations, we got two forms that we're going to be implementing. One of them, for the energy variable, we will be using the total energy. So that's kinetic energy plus internal. And then we have another one that I guess I'm going to call geophysical Euler or GFD Euler. But it's meant to be used, for atmospheric simulations. And the main difference there is that there's an assumption that gravity is involved, and we need a method that is that can preserve a state that is in hydrostatic balance, which in the current form, using the conservative form of the Euler equations and a total energy variable, that's incredibly hard to do. So our cheat for doing that is actually to follow what a lot of other people do in atmospheric science, is actually use a potential temperature variable for the energy equation rather than the total energy, and that ends up actually working out quite nice. But glossing over that will be the subject of what we talk about in coming live streams as we get those models together and get together the examples. So with this being said, let me see if I can embarrass myself with hopefully a video that is working. That's how, if it works, then I'm not going to be embarrassed. Then we're going to be smooth sailing here. So this guy we had like literally been running right before the live stream, so I have no idea what we're about to see here. Where did I think I put him up here. Linear pumpkin explosion. Let's see what we got. 5 seconds, so it must have done a lot more than before. Okay, so this is good. Looks like I don't have no normal flow boundary conditions turned on for some reason. I might have left radiation on when I did this one, so damn. But that's cool. Well, I hope at least, I had some questions about like, oh, can you guys actually do weird boundaries and or just yes, the answer is yes. It was, we do unstructured grids under the hood. I know up to this point I've only shown, looks like I'm using radiation boundary conditions. Damn it. Up to this point, I've only shown like stuff on structured grids. Underneath the hood, we're basically storing structured as unstructured. But this particular example, Garrett spent, I can't tell you how many iterations drawing pumpkins in Inkscape. But he's got a really cool tool called SVG to HokeMesh. Let's see if I can pull that guy up. SVG to HokeMesh. That you can use to draw a object or a set of objects in Inkscape, and then export the SVG into and convert it into a control file for the HokeMesh mesh generator. You're not familiar with HokeMesh, I advise that you get familiar with it because it's freaking cool. It does it's a quadrilateral and hexahedral mesh generator, so it does quads only in 2D and hex only in 3D. And it's maintained by the Trixie framework, but the primary author there is David Kopriva, and Andrew Winters has done a lot of work there as well. Garrett and I also contribute to this repository from time to time to kind of add features that are useful for self. It's just a really cool tool. And then basically once you go from SVG to HokeMesh, we use Hopper, the higher order preprocessor, to convert those to input files for self. So really, really neat workflow. We're working on tightening it up. I think we're going to add just native support for HokeMesh files so we can bypass Hopper. which would be nice. But Hopper is useful though, because if you have like Gmesh files, you can actually import Gmesh files into Hopper and then get those into Self. So there's just like so many things we got to talk about to like help you guys understand like how you can use this. I feel like kind of maybe walking through that pipeline of doing simulations might be useful. So if you let me say this, if you haven't subscribed yet, you should subscribe, because if you have a question and you want to ask it in the chat, you can do that if you're a subscriber. I am open to taking questions for the next few minutes. I don't have anywhere to be for a little bit. Yeah, if you guys have any questions on this, just let me know in the chat. Otherwise, I'll keep rambling, or maybe I'll play the. Damn it! I really wish I had turned on no normal flow boundary conditions. That's all I'm gonna kick myself for this. But hey, look, we get radiating sound waves leaving the domain. Oh, maybe it's actually is no normal flow. It just weakens out quite a bit as it spreads out. Shit, I need to just change the color map, because like it is bending around the objects. Like, what is going on here? Let me see. If I go, let me pull one of these PNGs up. If you guys don't have questions, you can just watch me look at pictures. That's cool too. Let's see here. That was nice. Thank you, Nicole. All right, cool, man. Nice quiet day. Oh yeah, so next week, we'll be out at supercomputing. So I won't be doing a live stream next week. However, I am interviewing a student tonight. I was going to talk about some combustion stuff. So you'll probably see that video sometime next week. It just won't be live. And then when we come back from supercomputing, Garrett's going to do a demo on SVG to hook mesh, like right before Thanksgiving. So things to be thankful for. Making meshes in Inkscape is definitely on my list. I'll definitely say that. So yeah, thanks everyone for tuning in. So happy to see you again. And I will catch you in a couple weeks. Yeehaw.